Hello everyone. We talk about our paper, Adversarial Distillation for Compact Generator. My name is Hideki Tsunashima. I belong to Waseda University. These are contents, background, proposed method, experiments, and conclusion and future work. Recently, generative adversarial net, as known as GANs, achieved impressive progress in generative models. One of the state-of-the-art GAN is Cygan. Face images generated by Cygan are indistinguishable from real face images. However, state-of-the-art GANs require large amount of computational resources. For instance, training Cygan needs 7 days on 8 NVIDIA Tesla V100. We cannot train Cygan easily. Moreover, the size of the pre-trained weights of Cygan is 310 megabytes. Cygan cannot be applied to an application of mobile devices easily because of large amount of memory consumption. Next, we talk about the conventional methods of complexing GANs. Firstly, we review the completion methods for unconditional generative models. LIT was proposed by Animesh et al. In 2019. LIT reduces chunks of the residual blocks so that it reduces parameters of GANs. However, LIT can be only applied to a generator of GANs which has a latent architecture. Typically, unconditional GANs do not have large latent architecture in comparison with classification models. Therefore, LIT cannot be applied to unconditional GANs. Secondly, Mse Method was proposed by Adversarial et al. In 2019. Mse Method takes the mean square error between the generated images of the teacher and student. However, Mse Method evaluates quality of the generated images from binary GANs. Namely, Mse Method cannot compress the generator of GANs effectively. Recently, several compression methods for conditional GANs are proposed. However, these methods are specialized to conditional GANs. Therefore, these are out of scope in our paper. We only focus on unconditional generative models. Next, we talk about our proposed method, AKDG. We propose adversarial distillation for generative models dubbed AKDG. The key concept is very simple but effective. The key of AKDG is the additional discriminator which judges a teacher or student. GS is the student generator. GT is the pre-trained teacher generator. Next, we talk about experiments. In experiments, we firstly confirm whether or not AKDG is effective. We conduct the comparison experiments on the 2D link and 2D grid dataset. The connection between modes is sparse in the student trained with AKDG on 2D link dataset. The student does not miss the mode in comparison with the binary model on 2D grid dataset. As a result, AKDG appropriately works. Next, we conduct the completion experiments using the real dataset. Inception score indicates quality and diversity of the generated images. Threshold inception distance indicates quality of the generated images. On the CIFAR-10 dataset, quality and diversity of the images generated by the student trained with AKDG is the best. Moreover, AKDG is robust in terms of the difference of architecture. The images generated by the student trained with AKDG is more distinguishable from the binary GANs. On the L3 bedroom dataset, quality of images generated by the student with AKDG is the best. AKDG does not work in case of small batch size, though AKDG indicates very powerful on the L3 bedroom dataset. We visualize the position of the images generated by the teacher and real images. We use UMAP, that is one of the visualization methods such as TSNI, after the real images and images of the teacher are encoded by inception V3. In the figure, the red circle indicates images of the teacher which does not overlap the real images. We sample the teacher images which have large gap from the real images when the small batch size. After that, the student generator receives long gradient from the additional discriminator. In the next iteration, the additional discriminator easily judges the images of the teacher or student because the student generator generates bad images. Finally, the raw student training heads for corpus. It is the reason of the why does not AKDG work in case of the small bat size. Conclusion and future work. We propose a novel completion method for unconditional generative models. In all experiments, our AKDG outperforms the conventional completion method. Future work. First, we will fix the problem of large bat size training. Second, we will incorporate other network completion methods such as pruning, quantization, and tensor factorization. Finally, we indicate references. Thank you for attention.